So hi everyone, it's really a pleasure to be here to see all of you 4 years after Grindelwald, and I hope this will continue for the future because I really think that we have wonderful discussions during these EPRV meetings. So today I will speak about HARPS-N, and I will not go into the details about what do we have, the subsystem and so on. I will really focus on the main troubles we had over the last 10 years because the instrument was first commissioned in 2012. So let's go directly into the core of the problem. So CCD warm-up. So this is where you warm up the CCD, you cool it down, and this is normally something you really don't want to do. Because of course, like you warm it up, you cool it down, it never goes in the same position, so you don't want to do that. However, the problem with HARPS-N is that we had a leak at the level of the cryostat, and after a few months, we're starting to see a lot of contamination of the detector. Here you can see a blue part of the spectrum where you see H and K calcium lines, so it's really the extreme blue in that case. But after a few months, you see clearly that the ghosts that we can see here are really much more important. And if you look to the background contamination on all the frame, it's really a mess. So the thing is that what we decided to do, in fact, is to remove this contamination. The only option was to warm up the detector. And this was happening every 6 months, more or less, over the lifetime of the instrument. So here you can see the general drift of HARPS-N over those last years with dozens of meters per second per year. Okay, it's nothing exceptional, I think. But you can see that at each warm-up that we were doing, we had jumps up to 80 meters per second in that case. And so a pixel is 800 meters per second, so this is 1/10 of a pixel. So you warm up, you cool it down, you are not exactly at the same position. And so what is the impact of this on the velocities? Here you can see the velocities of the sun over more than 7 years now, 8 years. If we just zoom in and we can see the warm-up positions here, we don't see anything obvious at the level of the meters per second or so when we do those warm-ups. So already this is a good thing. However, if, for example, we just compute the velocity of the sun using 2 different masks, one that put much more weight on the blue lines where we have more contamination that you can see here in blue compared to the orange one, and you use exactly the same spectra. So the only difference that you see is the difference between this line weight. And you see that we can reach up to 1.5 meters per second effect at the level of each, at the level of some warm-up, the worst one. But then if you use a line mask that have really weights of the lines that is corresponding to the radial velocity content on each of those lines, then we are much better than that. We are able to go down to like 20 centimeters per second. So although you don't want to do warm-up on your detector, it seems in our case, we were not so much affected by that. Then another big problem is how you deal with thorium lamp issues. And on HARPS-N, we are just using the thorium lamp to do the wavelength solution. So this is the 0 point of the instrument over the entire lifetime. And what we realized on HARPS-N, but also previously on HARPS, is that the thorium line drifts with time when the lamp is aging. And I will show you some results on that. And then also if you change the flux of your thorium lamp, thorium spectrum, you will see also some differential radial velocity effect. So each time you change the lamp, in fact, what you see, if you measure the position of the lines, you will see that there will be a small shift between those. So the lines are not exactly in the same position with a known lamp at the end of the age and a new one. And you see departure of about a few meters per second. But then what is interesting is that if you look at the argon lines that are supposed to move more than the thorium lines, you see also extreme departure there, dozens of meters per second. And one thing that we realize over all the lamps that we use on HARPS and HARPS-N is that basically there is a ratio of 10 between how the argon lines are moving comparing to the thorium lines. And so then what you can do, you are never able to measure what is the drift of the thorium lines over time because you use them for the wavelength solutions. So they fix the 0 point of your instrument. But you can see how the argon lines are moving relative to that. And here you can see on top that once we change the lamp, really go back to the level of the lamp when it was like new at the beginning of its use. And in the bottom here, you can see the velocity of a star, and you clearly see that at the length change, there is a big offset of a few meters per second. But knowing that the ratio between the change between the argon and the thorium is a factor of 10, you can correct for this effect, and then you are able to really like flatten out the velocity of stellar observation. Another thing important is also what I was saying before. If you change the flux of your thorium, you will have some effect in velocities. And this is just the flux compared to a reference. So it's percentage here, or just flux ratio. And we saw that during 2019, beginning of 2020, we were not very careful with this lamp, and we had some flux that went 4 times higher than the baseline. And here on top, you can see this flux ratio as a function of time. And in the bottom, you can see the velocity measured on one thorium line. And you see that you change by 10%, 20% the flux on the thorium spectrum. And this line here is moving by dozens of meters per second each time. And you can look to all the thorium lines, and some of them will show some really strong systematics, and some others are very flat. And I suppose what is happening is that some lines are contaminated by tiny blends. And when you change the intensity of the land, the intensity between this blend and the main line will change. And so you have really to be careful about that. If you derive the velocity without being careful about which line you use, on the top here, you can see the velocity of one star over 10 years. And in red, you can see what is the estimated effect of using these bad thorium lines. And you see a wonderful correlation between the two. And once you curate your line list and take the lines that are really not sensitive to those flux ratios, you arrive to something that is much better. So one thing that I want to say here, so I know that a lot of people use LFC now, but still there is the thorium as a backup. What we realize on HARPS and HARPS-N is that once you start to see this flux ratio that change significantly, it means that somehow the lamp is aging. And what you can do is that you can change the voltage of the lamp to stay at a constant flux ratio. And by doing that, you are able to save several years, at least on HARPS and HARPS-N, we were able to have lamps that was lasting for 5 to 6 years because we were really careful with that. Okay, finally, charge transfer and inefficiency or efficiency, depending how you want to call it. When you read out a detector, you have to move the electron from pixel to pixels, and along the way, you always lose some charge. Okay. And so there was a nice paper written in 2006 that explained very well this effect on the STIS detector on Hubble. And they were able to show that the CTI effect is a function of the background, but also as a function of the flux that you have. And it's inversely proportional of the flux. So in our case, for radial velocity observation and the thorium lines or Fabry-Perot lines that we use, we don't have so much background. But of course, if the flux change, we will see an effect. Here you can see if you take 2 back-to-back Fabry-Perot and you measure the drift between them, if the flux ratio is 1, you measure a drift of 0, which is normal, the instrument didn't move, whatever. Then if you change the flux ratio by a factor of 10, and you don't correct for this CTI effect, then you will see 10 meters per second offset. And then you can do this for different flux ratios, and you arrive to this blue curve. The more you go down in flux ratio, the more basically your velocities will be blue shifted. And in fact, this can be explained because if you compare 2 raw images, one corrected and one not corrected, at the level of a thorium line that we can see here, you can see that you have more electrons on one side of the line than on the other one. Because while you are transferring the charge, you are leaving some behind. So you create this imbalance at the level of each spectral line, which creates a radial velocity effect. We see the effect here on stellar observation. You go down in signal to noise, and you see that the velocity becomes blue shifted by dozens of meters per second, while after you are able to correct for this effect, then you have something much flatter. So this is also something important to consider if you don't get always the same signal to noise for each observation. Okay, just a few results about the 10 years that we have been observing like standard stars on HARPS-N. This is one of the stars that we have, 1.2 meters per second in that case. So this is really what is coming out from the pipeline without any post-processing or whatever. Then we have some tools to be able to do post-processing to remove instrumental effects that are very difficult to do at the extraction level. This is a nice work done by Michael Crétinier, a code called Yarara. And in that case, for this star, we're able to go to 0.9 meters per second. So I just want to emphasize that here we don't use any standard stars to correct for that. This is only based on the calibration of the instrument. Another star here, 1.4 meters per second. After post-processing, we're at 0.75 over 10 years. Another one, 1.4, 1.1 meters per second. And just here, another one, 1.3 meters per second in that case. We still see some systematics. On the 4 stars that are shown here, we can see that around this time, all the velocities are a little bit offsetted by a meter per second or so. We are still working on this issue. We know somehow it's coming from calibration, but we couldn't find yet the best way of dealing with this issue. But if you are looking at HARPS-N's data, be careful. This creates a 70 centimeter per second in 2000 days. So it's very like, it would be a very nice planet, but we see this on several of our targets. So there is still some instrumental systematics there. The sun, finally, on top, you can see the pipeline radial velocity. In the bottom, after processing with Yarara. What is nice is that, of course, the sun is active. So 2 meters per second, more or less, during the activity phase, 1.1 during the inactive phase. But after correction, in fact, we see that we are able to go down to 0.75 everywhere. So it seems that we are able to correct very well for activity, and we are really starting to hit the flow of stellar signals because the 75 centimeters per second, it's really what is estimated for supergranulation, and we don't correct for this effect yet. We don't have any ways. Okay, so there will be a talk after by Michael about how he was able to correct this for the sun. Okay, so perhaps one thing that I just want to emphasize at the end is that I think it's very important if you have a solar telescope on your spectrograph, because this really allows you to sample all the different systematics at all time scale. But the sun is not a standard star because there is the magnetic cycle. So you also need a few very simple stars, very simple standard stars to really understand the stability of your instrument over the long term. And although the first one is quite easy to get once you have the solar telescope, the second one is difficult because you have to do this by night. And of course, it requires really a specific schedule. So thanks a lot, and I will take a few questions.
Thank you very much, Xavier. Questions in the room? Yes, please.
So you mentioned that you have several years worth of lifetime out of a thorium argon lamp. That's very impressive. So you mentioned that you keep the flux ratio stable by reducing the voltage. At what point do you stop? So when do you say this is too old?
Yeah, so after a while, like you can change the voltage, but really at the end, you cannot really just, so you really see that it starts to drift away, and then it's really the moment where you have to change the lamp.
If there are no more questions, I have one.
Yes.
Oh, there is one. Sorry.
Do you still have old good thorium argon lamps, or are these already the new generation?
You have to ask this guy.
Don't answer, don't answer.
Now we have a few left, but really not a lot, I think. I don't know if you want to. No, but no, we don't have a lot.
Very, very few of them. We have like 2 to 3 left. Very quickly, did you try to look at different thorium lines from different ionization levels? Because they do behave quite differently.
Yes, indeed. So I remember I've talked with Christophe Lovis about that. In the new espresso pipeline, it just use lines that should be the less sensitive. In the end, we still see some effect there. So hopefully for HARPS and HARPS-N, we had really a 10-year baseline. So we were really able to, over those 10 years, see how they was behaving, indeed. But yeah, I published a list of lines that are very, very, very good to use in 2021.
Thank you very much.